Hello and welcome. Today is a bonus lecture. Is polar coordinates in mechanics. This topic is no longer in any syllabi, as far as I know. It used to be in Edexcel until mid 2000. It used to be in the old M6, or prior to 2000, it was in the old M4s, and only AQA other than Edexcel kept it. I can't quite remember if it was their M4 or M5 that it was until 2017 before this new spec, this piece of crap came into effect. So a lot of this now has been lost. So I'm going to try to give a non-analytical lecture of acceleration in polar coordinates. There will be very little reference to pure mathematics and polar. It's got not a lot to do with that. And I will make some connection possibly at the end with circular motion, which is like motion in a circle with a constant radius and constant angular velocity. So first of all, let's start with this diagram and let's see about how we differentiate vectors. So this is now, actually we don't really even need a picture. Okay, so let's say we have a position r is equal to some function of t in the I direction, plus some function of t, pardon me, in the j direction. And even from the very beginning, when you do calculus kinematics, in your very beginning of your mechanics, you say, okay, dr by dt, vector dr by dt, which represents, of course, the velocity vector, is f dash of t. You differentiate the bits in front of the I, and you differentiate in the bits in front of the j. And that's as far as you're happy, it works, and then you can do acceleration in a similar kind of way. I just want to point out, it's not strictly speaking correct what you're doing or how you see it, perhaps, although it is. These are products. So when you're doing your dr by dt, your velocity, you have a product rule. F dash of t, leave the I alone, plus leave the f of t alone, differentiate your I. Your I is a constant vector. It doesn't change. So on differentiation, it differentiates to 0. And similarly, you come to another product, g dash of t in the j direction, plus leave your g of t alone. But of course, the j on differentiation with respect to time will give you 0. And of course, this always happens. And we don't really need to sing a song about it. I don't have a problem if you write this. Absolutely not. That's how I see it as well. But it is not true for vectors in general. Okay, so you have to be very, very careful. This is only true for the vectors that we know for I and j. So let's look now at a different type of vector, which is not constant. So suppose we have some kind of origin, and we have a vector, and this vector here, let's say without loss of generality, that is called length 1, so it's a unit vector like the I and the j, and this vector is always radial. So this vector now r, which is in the r hat direction. Actually, shall I just bother with directions? Probably not. This is now a unit vector. I don't want to put a lot of notation here because it might complicate things. We got a unit vector, and this vector is always radial in its direction. It can take positions like that. Like when you're having, polar coordinates and you're drawing, it's always in a radial position. Okay, but always unit length. Okay, let's take off some of these positions. So quite clearly, this is not a constant vector. It depends on something. What does it depend on? Well, what it depends on is, in fact, on this angle here, theta, polar coordinates, of course. So we're going to try to differentiate this particular vector. We're going to call it r hat. And let's do it here. This vector r hat is, of course, we're familiar with i's and j, so that's ri, and that's our j direction. So we're happy to resolve it into I and j components, so we know how to differentiate it. And therefore, this is going to be, since it's unit length, 1 cos theta, 1 cos theta in the I direction, plus 1, I'm not going to be writing the ones eventually, just sort of wrote it there for completeness, in the j direction. So now I want to differentiate this with respect to some kind of variable. And the variable that I'm going to differentiate, these are functions of theta. So I'm going to do d by d theta of my r hat. Okay, how does that differentiate? Well, these are unit vectors, so I'm going to do the usual stuff that I'm used to from elementary mechanics. So cos differentiates to minus sine in the I direction. That is constant, there's no change. I don't need to be applying product rules. And sine will differentiate to a cos. And of course, that's going to be in the j direction. Okay, now what is that? Okay, it's more sines and causes. In relation to this vector, I mean, what is this? My claim is that, in fact, let me just write a little bit here. Minus sine theta I plus cos theta j is the same as cos theta plus pi over 2, we'll check it of course, in the I direction, plus, I'm looking at this bit here, sine of theta plus pi over 2 in the j direction. So in relation to the original vector that I started is a rotation by 90 degrees in an anti-clockwise direction. Let's check these bits and let's verify it does take us to cos theta plus sine theta in the I and j direction. So this will give us compound angle cos theta cos pi over 2, and then we got minus for a cos sine theta sine pi over 2. Cos of pi over 2 is 0, sine of pi over 2 is 1, and therefore that gives me minus sine theta, indeed. And similarly this one, sine theta cos pi over 2 plus cos theta sine pi over 2. Cos of pi over 2 is of course 0, sine of pi over 2 is 1, so that's cos theta. So indeed, I can actually write this as cos theta plus pi over 2 in the I direction plus the sine of theta plus pi over 2 in the j direction. So when I differentiate this vector, it's the same as rotating it by 90 degrees in anti-clockwise direction. Question, will it do it again? Of course, there's nothing special about the position being there. So if I differentiate twice, I'm going to do one more just for fun, d by d theta of my r hat. I'm looking at this line, differentiating is going to go minus cos theta in the I direction minus sine theta in the j direction. And again, let's check that now we have rotated, because we went from there to there, and then we're rotating by 90 degrees. We should be pointing towards the origin. So let's just double check this. The cos of theta plus pi in the I direction plus the sine of theta plus pi in the j direction. So this one will give us cos theta cos pi minus sine theta sine pi. Sine pi is 0, cos pi is minus 1, so that's minus cos theta. I don't know why I wrote the 1 there, which indeed it is. And if we look at this one, sine theta cos pi plus cos theta sine pi. Sine pi is 0, cos pi is minus 1, so that's minus sine theta, which indeed it is correct. So that is in fact cos theta plus pi in the I direction plus sine theta plus pi in the j direction. So that is rather interesting when it comes to non-constant vectors. This is what happens in the configurations. they rotate every time, whatever the vector is. If it's not constant, it has some kind of dependence, it will rotate by 90 degrees in an anti-clockwise direction. There might be scalar bits in there, extra bits that are being produced from the differentiation. Here, why we didn't have extra bits is because I differentiated with respect to theta, and there's no more change to come out of this differentiation of these quantities. But I kept it simple so you can see the concept. So this was like a unit vector. So let's return now to the polar coordinates and try to get expressions for the acceleration and the velocity first, and then the acceleration in polar coordinates. So this is my initial line, and we have, in order to determine position in polar coordinates, we only need to know, let's say I'll put the particle there so we're happy. Okay, so this is an angle theta. In order to determine its position, we need to know just the distance from the origin and the direction of the radial vector, because if you think about it, this vector depends on theta. Because I mean, when you're doing polar coordinates in your, I don't know, your pure maths, you just say the system requires two coordinates, it requires an angle, and it requires a radial distance. If you think about it, this radial vector, because it's not constant, it has embedded in him the theta. So if I move it somewhere else, so if I'm kind of like there, although it's a different theta, it's also a different r hat. Okay, and therefore it's just a way of writing this is my position vector r is some scalar r, this distance here, in the r hat direction. So this is the position vector. It's like saying r is equal to xi plus yj, so vector. So this is basically equivalent, only it requires an r hat. Let's differentiate that. So I'm going to get a velocity. A velocity is, of course, your dr by dt vector, which we write as r vector dot differentiation with respect to time. So this is a product now. We're differentiating the r. So this is going to give us an r dot in the r hat direction. And now we need to do the other way around. Plus r. Now we need to differentiate the r hat. Now the r hat is not a constant vector. The r hat is in fact a function of theta. Therefore, when we're differentiating with respect to time, it will produce, by the chain rule, a theta dot, and the vector will rotate and it will go in this direction here. And this direction we kind of tend to call it theta hat. In this coordinate system, you might see, I think ER and E theta vectors. These are the same. I call this R hat and theta hat. It's like your I and your J. And this, of course, will be in the theta hat direction. Okay, so this is now the velocity, and I'll come back to that in polar coordinates. I'm going to move from there, and I'm going to try to get acceleration. The acceleration is, of course, your second derivative of displacement with respect to time, which is the vector r differentiated twice. Differentiate your r dot with respect to time, because dots denote differentiation with respect to time. That's r double dot in the r hat direction. And now the other way around. Plus, leave the r alone. You're differentiating the r hat. Remember, that's a function of theta. So we're differentiating with respect to time. It will produce a theta dot, and the vector will rotate in the theta hat direction, from r into theta hat. Now we've got a triple product. It works exactly the same way if you haven't seen the triple product rule. Differentiate the first bit, r dot. Leave the other two bits alone, theta dot and theta hat. We go into the next bit. Leave the first bit alone, r. Differentiate the second bit with respect to time, theta double dot, another differentiation, and again in the theta hat direction. And now we have to differentiate the vector there. So that is r theta dot unchanged. Theta hat, the same way r hat depends on theta, so does theta hat. So it will produce another theta dot by the chain rule, and the theta hat will rotate by 90 degrees in an anti-clockwise direction. So it's going to go in the minus r hat direction, which is basically the r hat is radially outwards, the r hat is radially inwards. Let's tidy this up a little bit. R double dot, we got some r hat vector, so it's that bit here and that bit here, minus r theta dot all squared in the r hat direction, and we got two lots of r dot theta dot plus r theta double dot in the theta hat direction. This is the acceleration in polar coordinates for a totally unconstrained particle. So you can think of, I don't know, some star, some, I don't know, spaceship or something that has its own engine. And of course, not only it feels the effect of the force towards the star, but also maybe its engines are being fired in some kind of bizarre direction. So the path that it's following, it might be elliptical, it might be kind of like some arbitrary path. It's not necessarily going around in a circle like in a simplistic model. So this quantity gives the acceleration in the two different mutually perpendicular directions. Often this bit here, for reasons I might be complicating things too much now, we can actually write it as 1 over r d by dt of r squared theta dot. I think, just double check that this is the same. 1 over r, differentiate with respect to time, that's going to be a 2r r double dot theta double dot, and then differentiating the other one, r squared theta double dot, and then cancel one of the r's, 2r dot, because that's the 1 over r, plus r theta double dot. Yeah, it's the same. So we normally write it, if you look at the old formula booklets or some kind of reference thing, they might be writing this in this format, because that actually is more useful in kind of like problems that involve just central forces. If, for example, there is no transverse force, in other words, no force in the theta hat direction, this thing here, it represents the angular momentum per unit mass, and this will be a conserved quantity, so that will be a constant, and then it's all sorts of like calculus. So I'm not going to do problems at the moment or anything like that. That's as far as I'll take it. And I just want to point out a couple of things about circular motion that, as you know it from your kind of like further maths now, as it has been reduced to. So when something is moving in a circle of constant radius with constant angular velocity. So this is constant. So it's going around in a circle on a plate, rotating on a rod and so on. In this particular situation, these things here still apply. And you will see in a second, because of course that's the more general model. This takes over absolutely everything. So if you look at something which r is equal to a, where a is constant, then quite clearly r dot will be the same as r double dot will be equal to 0, since it's a constant. The same way, if the angular velocity is omega, which of course is again constant for this simplistic model, then the theta double dot will be 0. And let's see what this quantity is now reduced to. The velocity, this is the velocity expression. It says the velocity in polar coordinates would be r double dot, which of course is 0 in the r hat direction, plus a, because that's constant, omega in the theta hat direction. So if you're moving around some kind of circular plate, you have no velocity in or out, you stay at the same distance in the radial direction, and your velocity is simply A omega, as you know it, of course, in the radial direction. Not the radial, in the kind of like transverse direction, the tangential direction. Let's look at the acceleration. Let me just wrap this off, and let's look at this line up here. 0 minus A, and theta dot is omega squared in the r hat direction, plus this is of course 0 because r dot is 0. This of course is 0 because theta dot is 0. So the acceleration, if you're on the simplistic setup, is going to be just simply minus A omega in the r hat direction. Is that something we recognize? Of course, this is what we are being told. And this is why, I don't know if you've seen my stuff in circular motion. I'm very old school. So, you know, when you are marking the acceleration, always like this. Why is that? It's because this is r, therefore r dot and r double dot must be in the direction of r increasing. R increases that way. This is your r hat direction. Therefore, the acceleration must be marked in this way. But is magnitude, when I substitute, so I'm doing mr double dot is equal to blah, 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 blah. When I'm substituting the r dot, then I'm marking minus A omega squared is equal to dot, 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 because that's the correct way to make the calculus work. A lot of people and a lot of teachers kind of like they do a bit of a fuzzy sort of thing, and they just call it straight away into a plus. But occasionally I have found by adopting this technique, you can make mistakes occasionally, but the problem is not there. It's when you move to further sort of like more advanced kind of stuff at university, or you're mixing other system, everything goes completely pear-shaped unless you're using the kind of like the orthodox approach. Anyway, I've had enough of this lecture, and I'm sure you had enough. I don't know if anybody kind of like followed anything of what I've done in here, because it was quite intense. I mean, if you imagine back in kind of like in the year 2000, this would have been on the 6th module of mechanics. So you had M1, M2, M3, M4, M5, and M6. Hardly anybody done M6 unless you were doing triple further maths, essentially, because you could do it in those days straight maths, further maths, and additional further maths. You could have done 3 A levels in maths and nothing else. Good old days. Anyway, I'm just chatting a lot of rubbish at the moment. I hope you find this interesting. I'm going to be signing out, and I'll see you real soon. Bye for now.